Now watch this. A system is having 3 user process, each requiring 2 units of resources capital R. Which means, okay, resources are of generally two types. One is single instance and other is multi-instance type. For example, single instance means CPU. A CPU will be available only as one unit, right? And at any time, only one process will be able to use CPU. In general sense, right now we have multi-core, quad core, dual core, octa core, everything is there. But then typically what happens is CPU will be single instance and other resources may be many. For example, a system might have 4 printers, right? So what happens is, what is the difference between single instance resource and multi-instance resources is, if I have 4 instances of a resource, then simultaneously 4 processes can make use of the resource at the same time. That is called as multi-instance resources, right? For example, if you consider registers in a computer are many, right? And maybe files in a computer are many, right? So likewise, some of the instances are going to be multi-instance and some of the instances are going to be single instance. For example, memory is single instance and CPU single instance, like that. So now most of the questions that occur in this deadlock are with multi-instances. Sometimes they will talk about single instance also, we shall see that, but most of the times we discuss about the multi-instance. Now they are saying that a system is having 3 user processes, which means we are having 3 processes and each process requires 2 units of a resource R, which means in order to finish its execution, it needs 2 units of resource R at the same time, not one after the other. At the same time, it has to hold 2 units of the resource, then the minimum number of units of capital R such that no deadlock will occur. This is an interesting question. If this is the case, if there are 3 systems, right, and then if each one everything requires 2 units, then how many resources do you want so that there will be no deadlock? And obviously, one thing is for sure, if 3 users are there and each user requires 2 processes, obviously if 3 into 2 is there, then it is 6. If I have 6 resources, then there is no problem, there will be no deadlock at all. But if you observe this, the question is about, they are talking about the minimum number of resources. That is what they are talking about. It is not, 6 might not be minimum. Now what will be the minimum number of resources? Maybe why don't you try with 2 resources? If I have only 2 instances of R, right, then what happens? Let process P1 take the 2 instances of R and finish it, and then process P2 take 2 instances of R and then finish it, and then process P3 take those 2 instances only and then finish it. Therefore you might think that maybe 2 instances are also sufficient for the successful execution of all these 3 processes, one after the other. But then there is a problem here, right? The problem is, if you have 2 instances, if P1 takes 1 instance and P2 takes 1 instance, and now P1 will want the other instance and P2 will want the other instance, then what happens is they both will fall in infinite that waiting, which is nothing but deadlock. So there is a deadlock possible with 2. What happens if I have 3 instances? If I have 3 instances, then I'm talking about the worst case. See, this will not happen all the time, but then if there is a chance that it might happen, then it will happen. That is why I'm just analyzing it. So if I have 3 instances, then what happens is, again deadlock is possible. I'm just showing you that possibility. One instance will be taken by this, one instance will be taken by this, and one instance will be taken by this, right? Now what happens? All the processes are going to take these many instances, right? I mean 1, 1, 1, and then they will wait for one more, and all of them are going to fall in deadlock. Therefore, even if you have 3, there is a chance of getting the deadlock. Maybe if I have 4, then is the deadlock possible still? Let's see. If this one takes 1, this one takes 1, this one takes 1, still I'll have one more free resource, right? And I could give it to anyone, and then that will finish the execution. And after that finishes the execution, I'll give it to next one. Therefore, 4 is the minimum number of resources which are required for the deadlock free operation. So there are 2 types of questions possible. What is the maximum number of resources which will still cause a deadlock? So it is 3. See, if I have only 1 resource, right, obviously there will be deadlock. And if I have 2 resources, there is deadlock. And if I have 3 resources also, there is deadlock. Anything above 3 is not a deadlock. So in order to answer this such a kind of question, what you should find out is, see, they are asking about this. What is the minimum number of units of R required such that no deadlock will be occurring? What is the minimum number of resources required so that no deadlock will be occurring? In order to answer this, what you should do is, what is the maximum number of resources required so that there will be a deadlock? You answer that one and then you add +1. That will be minimum number of resources required so that there will be no deadlock. Okay, I'll take more examples and explain you. See, watch it. Now, let us say there are process P1 and process P2 and process P3, and this process P1 requires 2 resources to finish its execution at the same time simultaneously, which means it is not going to use a resource one time and release it and then next time. No, it is going to require the 2 resources at the same time. And assume that process P3 has P2 requires 3 resources and process P3 requires 4 resources. Then how many resources are required in minimum so that there will be no deadlock? In order to answer this, you should find out how many resources at maximum, even if provided, will cause a deadlock, right? So what is the worst case that they will fall in a deadlock is, since it requires 2 resources, if I assign 1 resource and this one will keep on waiting for the other one. And since it requires 3 resources, and if it gets 2 resources, this will wait for 1 more, right? And what about this? Since it requires 4 resources, if I give it 3 resources, it will wait for 1 more. And if I make such a kind of assignment to all these 3 processes, and all these 3 processes will now be falling in a deadlock, isn't it? So the maximum number of resources which will still cause a deadlock is 1 plus 2 plus 3, which is nothing but 6. So even if I have 6 resources, deadlock is possible. This is the maximum number of resources which will cause the deadlock, right? And if I add 1 more, which means if I give them 7 resources, then what happens is, even if this kind of worst case assignment has happened, right, this 1 resource can be given to any one of them and they will come out of the deadlock and the other one will also get solved, right? So how do you answer such a kind of question is, there are 2 types of questions here. They will say that each process requires so many so and so instances, right? And now you should see that give them everything that is required except 1, therefore they will wait for it, right? And you keep on doing it, which means give them all the resources they require except 1, just hold 1 resource back, then they will all fall in infinite loop, I mean the deadlock. And now that will be the maximum number of resources, even after giving which the process will be in the deadlock. In order to break this deadlock, minimum how many you want is 1 more, right? That is how you compute it. Let us say, what I mean to say is this. See this? Let us assume that P1, P2, P3, so on, Pn are the process, right? And each one requires x1, x2, x3, so on, xn resources in order to finish their execution. Then now the question is, what is the maximum number of resources? Even allocating those many, there could be a deadlock, which means what is the maximum number of resources which might still lead to a deadlock? If that is the question, then what you should do is, you try to allocate all the process, all the resources, but then hold 1 back, so that will wait for the resource, right? Which means if you have n all these n, let us say sigma, okay, without using sigma, then what I do is, I'll assign exactly x1 minus 1 resources to P1 and x2 minus 1 resources to P2, so on, xn minus 1 resources to Pn. Now if I have these many resources, then also there will be a deadlock, right? Therefore how many resources are there totally? Sigma I equal to 1 to n xi, which means I am adding all this, minus n, right? Even if I have these many resources, still there is a possibility of deadlock. This is the maximum number of resources, even after giving which there will be deadlock. Anything less than this, definitely there will be deadlock. Got it? So here I am saying that 6, even after giving 6 there will be deadlock, and even if you give anything less than 6 there is deadlock. See, even after giving 6 if there is deadlock, if you give less than 6, how can there be no deadlock? There is definitely deadlock. And if you cross this point, that point is important, below which there will be deadlock, above which there will be no deadlock, right? So therefore, what is the minimum number of resources so that there will be no deadlock, which means you have to add +1, remember this. I mean, you need not by heart it, is all logical, right? So always whatever the process are asking, give them as many as possible and hold one back, right? Then all of them are going to wait for that one more, right? Then everything is going to fall in deadlock. Then in order to break the deadlock, you have to just give one resource, and that resource can be taken by any of the process, and that will release all the resources once its usage is over. And once they release all the resources after their usage, you can take any one and then give it to the next one, give it to the next one, next one, next one. Like that you can break the deadlock. Got it? So this is one kind of question. Other kind of question possible may be, instead of asking about the resources, they can ask about the process. They will say that, okay, see this, I'll just change the question, it is just logical, you try to answer it. They'll say that we have a resource and we have 10 instances of the resource, 10 instances. Then if every process requires, okay, now let's not take 10, let's take 6. Now they are saying that there are 6 instances of the resource, right? And every process PA requires 2 instances to finish its execution. Then how many processes can be present at maximum so that there will be no deadlock? Okay, are you understanding this? They are saying that we have 6 instances of a resource and every process requires 2 instances to complete its execution. Then how many processes can be present in maximum in the system, therefore there will be no deadlock, in such a way that there is no deadlock. Then how can you solve it is, you find out the minimum number of processes, right, that can be present inside the system which will lead to deadlock, and then you subtract -1. It is very logical, try to understand this. See, now the question is, number of resources available is 6 and each process requires 2 resources. Then the question is, how many processes can be present at maximum so that there will be no deadlock? Now what I try to do is, how many processes are required at minimum so that there will be deadlock, right? Then see, if there are 6 resources, right, then how can a deadlock be possible? If every process requires 2, deadlock will be possible only when all the processes take 1 instance each and wait for the other instance, isn't it? Deadlock will be possible when all the processes take 1 instance each and wait for the next instance, right? How is it possible? If P1 takes 1 instance, P2 takes 1 instance, P3 takes 1 instance, P4 takes 1 instance, and P5 takes 1 instance, and P6 takes 1 instance, then all of them have taken 6 instances, right? And now they need 1 more instance. Therefore, the minimum number of processes because of which there will be a deadlock is 6. If you have anything less than this, right, there will be no deadlock. Is it minimum or maximum? The minimum number of processes which are required so that there will be a deadlock is 6. Is it visible? Right? So watch it. So if you have 6 processes, then only there will be a chance of deadlock. If you have anything less than 6 processes, there will be no deadlock. Are you getting this? The reason is, if I don't have 6, if I have only 5, then what happens is, even if all of them takes 1 each, there will be 1 more free resource, and which can be taken by any one of them and they will get freed up, right? Therefore, the minimum number of resource, the process which will lead to deadlock is 5 here, right? And so what is the maximum number of process which will cause no deadlock? Then -1, isn't it? So the maximum number of process which can operate without deadlock is 5. Getting this? Okay, let's solve one more example. Let us assume that the number of resources available is 8, something like this. Let us say the number of resources available here is, instead of 6, let's keep it 6 itself. The number of resources available is 6, and then each process requires 3 instances of a resource to complete its execution. Then my question is how many processes can exist in the system without any deadlock? Then how can you solve it? Find out the minimum number of processes which can exist in the system because of which there could be deadlock, right? So what is the minimum number of process? If each one requires 3, then what I do is, I'll assign to each process 2 instances, and I see that they will definitely fall in deadlock, right? And then the third one takes 2 instances. Therefore, if I have 3 processes, right, then definitely there is a chance of each one falling in deadlock, isn't it? Why? If I have only 2 processes, then definitely it is not possible. If I have 3 processes, definitely these 3 are going to take 2 to each and they are going to fall in deadlock. Then how many processes can be present at maximum in such a way that there is no deadlock is 2, isn't it? Why? If I have 2 processes, then even if they take up 2 to each, right, and they are waiting for one more, we have 2 more resources and they can successfully complete. This is one kind of question possible. So they can tell you how many processes are there and what is the need of each process, and then they can ask you how many resources are required. Either there is a deadlock or either there is no deadlock, or they'll give you the resources and then the need, and then they'll ask you how many processes are required to break, so that there will be deadlock or there will be no deadlock. If you want one more example, let's see this. Let us assume that the number of resources we have is 100 and each process requires 2 instances. Then how many processes can be present at maximum so that there will be no deadlock, right? Can you guess it? How can you guess it? See, now you just find out how many processes can be present at minimum so that there will be deadlock. First you guess that. So minimum number of processes required for the deadlock is 100, isn't it? Why? If each process takes one instance each, right, then all the resources will get held up and no one will release the resource, and therefore there will be deadlock because every process will be waiting for one more. So if I have 100 processes, there will be a deadlock. How? Every process will take one resource each, and therefore other process will be waiting for that, every process will be waiting for the second resource. So the minimum number of processes which will cause deadlock is 100. If you have anything less than 100, then that will not cause a deadlock. Therefore, the maximum number of processes that can be present which will not cause a deadlock is 99. Are you getting this? Okay, I don't know whether you got it or not. Let's do one more. Now let us say the R is number of resources is 100, okay, and now let us assume that each process requires 3 instances each. Then how many processes are required at minimum so that there will be a deadlock? Then how can we do it is, if there has to be a deadlock, what should happen? Every process should wait for one more resource, right? Then what I do is, I'll give to every process I'll assign exactly the number of resources required minus 1. So I'm going to assign 2 processes to everyone, so that 2 resources to each one, so that all the processes are combinedly going to take 100 resources, right? Then what happens? It is nothing but 50, right? So if there are 50 processes present, all of them can take 2 resources each and they will consume all the resources available. Therefore everyone will fall in deadlock. Now in order to break this deadlock, if 50 processes are the minimum number of processes to ensure that there is a deadlock, then anything less than 50 there will be no deadlock. Then what is the maximum number of processes because of which there will be no deadlock? I mean, even after having those when there is no deadlock, it is nothing but 49, isn't it? Are you understanding this? Maybe if you didn't understand it, you could do one more question. See this. Assume that instead of this 3, let us say 4. Each one requires 4 resources, right? Then how many processes can be present at maximum? Now what did I say? You try to have as many processes as possible and give them all the required resources except one, so that they will wait for that one particular resource and they will fall in deadlock. So in this case, what happens is Pi, I am going to decrement Pi minus, see this one, 3. I am going to give 3 resources each to each process, and I am going to introduce n processes in such a way that all these processes, when they take up 3, are going to hold all the 100 resources, right? Then how many do you get? So n equal to 100 by 3, right? So should I put ceil or floor? That depends. Actually the question is, I told you, right? So whenever I say that it is the minimum number of processes required, always it is ceil. Whenever the question is about minimum, it is always about ceil. Whenever the question is about maximum, it is always about floor. Now I am talking about minimum number of processes required so that there will be a deadlock, right? So how many processes will be required? It is, I think you will get 33 point something, right? Therefore you can write 34. So how is it possible is, for 33 processes you assign 3 resources each, therefore they are combinedly going to take 99, and for the 34th process you assign just one resource, right? For the last process, 34th one, you assign just one resource, therefore one resource is taken up. That is how all the 100 resources are engaged, right? Now there are 34 processes required which will take up all the resources available, and still they will lead to the deadlock. Therefore minimum number of resource processes because of which there could be deadlock is 34, and anything less than 34 deadlock will not be possible. Therefore what is the maximum number of processes that can be present without any deadlock? It is 33, isn't it? Therefore maximum number of processes with is 33, for which there is no deadlock is 33. I hope that you understood this. Anyway, I am not thoroughly convinced that you are following it, because whenever I teach it in the class, people generally get confused at this part. So I have taken lots of examples. Maybe I'll do one thing, I'll solve even more examples just to be sure. If you understood this, you please skip the video. If you didn't understand it, you please continue watching. I'll just keep on taking more examples, okay? Because I'm just not convinced. Okay, now watch it. Let us say I have 100 resources, and each process wants 5 instances of the resource to finish the execution. Then what we should do is, then the question is again same. What is the minimum number of processes that have to be present in the system because of which there could be a deadlock, right? If deadlock has to happen, then what is the procedure? Try to assign every process as many resources as they want except one, so that they will wait for that particular one and they will consume all the resources. Now every process I'll just assign 4, so that they will wait for the new one extra. And then how many process I'll put the number of process in such a way that all these processes are going to take up our resources completely, right? Then what is n? N is 25. What does it mean? The minimum number of processes because of which there could be a deadlock possible. The minimum number of process because of which there could be a deadlock possible is 25. How? If all the 25 processes are going to take 4 each, they are all going to combinedly wait for one more resource, and one more resource is not available, right? Therefore they are all going to wait for one more resource. So if this is the minimum number of processes which will lead to deadlock, it means that if you have anything less than these many processes, there will be no deadlock, isn't it? Then what is the maximum number of processes that can be present inside the system for which there is no deadlock? It is nothing but 25 minus 1, which is 24. Got it? So there are two types of questions possible. One kind of question is, given the processes and then given the requirement of each process, how many resources are required so that there will be no deadlock. And the second one is, given the resources and then given the instances required, how many processes can be present so that there will be no deadlock. Anyway, we don't want any deadlock to happen. Okay, I'll take few more examples. Okay, now watch this. Let us assume that there are 10 processes. See this? There are 10 processes, and each process requires 3 instances of a resource. Then how many resources are required? At minimum, how many resources are required so that there will be no deadlock? Then how can you find it out? You have to find out the maximum number of resources required so that there will be deadlock, right? And then you add one more, there will be no deadlock. Now see this, how can I find out maximum number of resources because of which there will be deadlock is, now I want to put all the process in deadlock in such a way that they will not come out. So see this, if I have 10 processes and if everything requires 3, and if I assign them 2 exactly, right, then what happens is, now if I assign 2 resources to 10 processes, combinedly they are going to take 20 processes and still they are going to be in the deadlock, isn't it? Therefore maximum number of processes which will still lead to deadlock is 20. then if I give them one more resource, then there will be no deadlock, right? Therefore minimum number of process because of it there will be no deadlock is 21. Okay, so I don't know whether you understood it or not. Fine, I'll take more examples. See this, what I'm trying to do is, again I'll explain it. Let us say there are 10 processes present in the computer, in your system, and now each process requires 2 instances. How many did I take? 3 instances, right? Each process requires 3 instances of a resource, right? And now the question is, how many resources are required, at least minimum number of resources required, so that there will be no deadlock. Why are we talking about minimum number of resources? Because we always obviously want to conserve the resources. We don't want to give nearly 30. If I give 30 resources, see, if every process requires 3 resources and there are 10 processes, if I give 30 resources, obviously there will be no problem at all, right? But then I don't want to waste this much money. What I wanted to do is, I want to give them as little resources as possible, still so that there will be no deadlock. Now what I try to find out is, in order to solve this, whenever they are asking about the minimum number of resources because of which there will be no deadlock, I'll try to find out maximum number of resources because of which there could be deadlock, right? So one thing is for sure, if there are 10 processes and if you give them 1 resource each, definitely with 10 resources there will be deadlock. But that is not what I'm interested. What I'm interested is, how many maximum can I give them so that still they can fall in deadlock, so that I can give one more and break it. That is what I wanted, right? Now if every process requires 3 resources, now if I give them 2 resources each, which means if there are 10 processes and if every process requires 3 resources and if I give them 2 resources each, then what happens, combinedly they will all take 20 resources and they'll all be in a deadlock in such a way that even if you add one more resource, the deadlock will be broken. Therefore this is the maximum number of resources which will still cause the deadlock. Then what is the minimum number of resources which will break the deadlock? 21, isn't it? Are you getting this? Now let's extend this. Let us say the number of processes are 100 processes are there and each process requires 5 resources. Then how many resources are required at minimum so that there will be no deadlock? Obviously if you give 500 resources there will be no problem at all, but then I don't want to go till here. See, here also obviously if you give 30 resources there will be no deadlock, but then the minimum required is 21. With 21, if they are able to survive, why do you want to give them 30 and waste the money, isn't it? We can even decrease the cost. Here 500 if you give them, they will be happy, but then you will not be happy, right? So let's see what happens. Now I want to find out maximum number of resources even after giving which there will be a deadlock. Then I'll find out minimum number of resources which is going to break the deadlock, right? Now what is the maximum number of resources even after giving which there will be deadlock? Now if I assign 4 resources to each process, that is the maximum I could assign, and still keep a process waiting for a resource. Now if I assign 4 resources to each process, and since there are 100 processes, the total number of resources required, assigned will be 400, and even after taking 400 resources, all these 100 processes will still be in deadlock. Now if I have to break this deadlock, I have to just add one more resource, which means if I have 401 resources, right, then there will be no deadlock at all. Got it? Deadlock will be broken, right? Therefore the minimum number of resources required to break the deadlock is 401, not 500. Got it? So this is how you could find it out. Even in that case, you understood that. So I'll take, instead of taking all the resources to be equal, let's answer this one. See this? Let us say the requirements are like this. P1 requires 20 resources to finish its execution and P2 requires 30 resources to finish its execution. Okay, let me keep the addition simple. P1 requires 21 resources to finish its execution and P2 requires 31 resources to finish its execution and P3 requires 41 resources to finish its execution. Then the question is, what is the maximum number of resources even after providing which there will be a deadlock? Or let us ask the other question, what is the minimum number of resources that have to be given to this system so that there will be no deadlock, right? In order to answer this, what is that you are supposed to find out? What is the maximum number of resources even after giving which there could be a deadlock? After finding out that number, you just add one more and the deadlock will be resolved. So now I am talking about what is the maximum number of resources that could be given to this system so that even after giving those many, the process should still be in the deadlock. Now what I do is, I'll try to give them as many as they want except one, so that they'll wait for that one resource and fall in the deadlock, right? So what happens here, for P1 I'll assign 20, and for P2 I'll assign 30, and for P3 I'll assign 40, right? Now all of these put together, it is going to be 90, right? Now even if I give 90 resources, right, still there is a chance of deadlock. Anything less than this, there will be deadlock. Even if you give 90 or anything less than this, there will be deadlock. Anything above this, the deadlock will be resolved. The reason is, even if they take the resources like this, still we will have one more resource, and that one resource can be taken by anyone, right? Therefore, what is the minimum number of resources required so that there will be no deadlock operation here? 90 plus 1. That is how you could solve it. I mean, you could derive the formulas and then mess it up. If you want to derive the formula, I have already derived it, right? So how did I derive it? If every process is having a need of xi, pi is having a need of xi, and if there are n processes, then what you do is, you have to find out the maximum number of resources which will still cause the deadlock. How can you find it out? Simple, xi minus 1, x1 minus 1, x2 minus 1, x3 minus 1, right? Which means it is nothing but sigma I equal to 1 to n xi minus n. Why minus n? Because from each xi I am going to subtract 1. Okay, if you didn't understand it in the previous example, I am just explaining you. It is a simple question, but I don't know why people get confused in the classroom. So I am just cautious here so that you will understand everything perfectly. That is my main concern. So see this. Now I am saying that a process pi here, process pi, it requires xi number of resources. Then what is the maximum number of, and then there are 1 to n processes, which means I is running from 1 to n. Then what is the maximum number of resources, even after giving which there will be a deadlock? That is what the question is. Then what I am trying to do is, I'll try to give them as many resources as possible. So what is the maximum requirement by x1, p1, that is x1, right? I'll give them as many resources as possible, but then I'll just hold back one, so that P1 will wait for that one resource and fall in the deadlock. Similarly, I'll give process P2 all its requirement except one. So on, I'll give the process Xn all the resource process Pn all the resources it needs except one, isn't it? Then what happens? If I add them all, it is going to be C. From x1 I subtracted 1, from x2 I subtracted 1, and from xn I subtracted 1. Therefore, from the complete sum I have subtracted 1 n times, right? So sigma I equal to 1 to n xi, it is going to give all the x1 plus x2 plus x3 sum minus n. This is the maximum number of resources, right? Even after assigning which there will be a deadlock, right? So after even assigning these many resources, there will still be a deadlock. Now what is the minimum number of resources, because of which there will be no deadlock? Then you have to add plus 1. Got it? This is the answer. Anyway, don't remember the formula, don't by heart it, is just logical. You try to derive it, use your common sense and derive it. See, in GATE or anywhere, never try to by heart anything. Everything is logical. You should be able to derive it on the go, right? So these are the two kinds of questions which are popular on this. I hope that you understood it, or maybe I'll take and solve the GATE questions. You'll understand it better, right? Fine.